Okay. Hi, guys, and welcome back to another EMP session. Um, so for today's session, we're just going to be covering one topic, but it's kind of an important topic. It's another data structure that you guys have been learning about, and we're going to do like an in-depth review of the data structure and what it does and how it works, and then we're going to spend like the second half of the class just working on some um, practice problems. So yeah, so no learning objectives that we've got on here today. Remember that you can follow along on the course website here, and all of the slides are available at the Netify app website, which you can use if you want to see the starter code and use that in your example. All right. So today's topic is linked lists, but let's talk about array lists before, right? So in order to understand kind of the difference between them and also understand how the different operations work underneath the hood, it's good to talk about array lists before we talk about linked lists. So remember that in general, when we're talking about these things, we're just talking about different implementations of lists, right? Sorry, not the right one. Talking about different lists. So you can just think of it like traditional list, and then you put things in here, right? Like numbers, for example. In Java, in Java and other programming languages also, you can program your list to work in different ways. An array list is one of those ways. Linked list is another way. So for array lists, we've looked at some operations: add, remove, get. And we've looked at how to write those in code, and then maybe we want to take a look at how fast it is and how does it look under the hood. So first, let's talk about array lists and adding elements to an array list. So here's a nice little diagram that we've created of what an array list looks like. So there's an array list of persons. This is the actual array, and then each of the blocks has an index, and it points to the reference for an actual person object. Okay, pretty self-explanatory, I think. And now let's see what happens when we try to add something to it. Okay. So here, let's break this image down, kind of more complex, I think. And this is the original list right here. When the new array list is created and when the new item is added, you kind of have to move all of the indexes from where they were originally. You have to move them down one, like so. So you're moving each of these down one. So you're creating a new array list. You're moving each of these pieces over one, and then you're creating that new person at the beginning. So those are kind of the steps that go into creating this, right? We nudge everything over by one, add an element at the beginning. And that's kind of a tedious process, right? It's kind of annoying to have to move everything down. Like, think about this in terms of code. Like, if you were to implement this, like, let's say array list didn't come with like an add method. If you were to implement this, it would kind of be annoying just because you have to loop through each of these items, move them over to the next index, and create this new person at the beginning. So that's because this array was a fixed size, and in order to add the other element, we have to move everything over, right? So we can consider the operation of adding elements to an array list to be O of n, because the steps that go into it are to create a new array, which is constant time, and then adding elements, and then moving the elements down one index to be O of n, that's linear time, and then finally adding the new element, which is constant time. So ends up being O of n because of kind of the biggest operation that happens here. So that is kind of an overview of what happens under the hood when we are adding a new element to a linked list. An array list. What happens with linked lists, we'll talk about a little bit further down the line. But let's take a look at what happens when you remove an element, a particular index. Okay. So this is the same initial array list as before, but now it's just like a slightly different setup for what happens when we're trying to get an element from the linked list. So when we're trying to get the element, let's say that we're trying to get the person at index 4. We get this index, and then we return that back, right? And you can think about this, and maybe it's not very intuitive to see from the image, but there's not a lot of like moving objects around. There's no iteration through the array. You're just kind of directly accessing it. So this makes it really fast and easy to do. So it's constant time, O of n, really quick access. You just directly access it. Now we'll see later on that it's a little bit more difficult to access elements in a linked list than an array list. So quick recap, accessing the element for the array list, O1, so constant time. That's fast. It won't be this fast in linked lists. All right, so that looks like we're pretty much done with the array list section. Kind of breeze through that. Any questions? Okay, cool. Good. So now let's compare those operations with the linked list, right? Adding the object to the beginning of the linked list. Remember, when we looked at this from the perspective of an array list, it was kind of tedious. It was O of n. So here's our linked list right here. We've got some values here and a reference to the next slot. So kind of built exactly how you'd imagine it. It's a set of linked lists. The values point to the person objects, the next points to the next value. Just keep in mind that linked lists can be kind of singly linked lists or doubly linked lists. They might only have the capability to look at the next element, or they might have the capability to look at the previous element. So in this setup, there's only one of those capabilities, the ability to look at the next element, but you could have a previous here and it could point back to the previous element. And then in some cases, you might even see a circular linked list where the very last element ends up pointing to the first element. But in this course, you won't be getting that complicated. It's kind of very simplified. You're just getting a chain of item objects. And again, they have two values, two like things inside of each of the objects, a value and a next. And yeah, the end of the linked list is indicated by the null value when next points when x is equal to null, then that's when you know that you've reached the end of the linked list. Right, so let's take a look at adding. So here, when I'm adding a new element to this linked list, sorry, what is happening, right? It's very kind of easy. So you have this initial linked list, and now you're just pointing it to this value here. But now values next. So this is like the new element that you're adding to the linked list. So now values next just points to the previous first element of the linked list. But you don't have any of this kind of shifting all of the units down. You're just kind of moving what this points to. This points to the new object, and you're pointing what the new object's next points to, which is this object. So you don't have to move any of these elements. Kind of seems like a faster technique than the first one, right? That's because it is. This is a constant time operation. It's just a fixed number of steps, no matter what the size of the linked list is. You just have to add this first element, and you don't have to move anything else down. So compare that with the array list, which is linear time. Then this is constant time, so it's faster. So we looked at adding. Let's talk about retrieving the element. Get operation. So let's say that I wanted to get the person at index 1. So I guess you guys can't see this super well. Okay. The person at index 1, we have our linked list here set up like this. So I say, okay, this linked list just points to the first element, right? And when I'm here, I can just check to see what the index is. If the index doesn't match, then I have to move to the next one. And then I get here, and then I'm like, okay, I found the element that I was looking for. And then I can just return that. So kind of an annoying process, because think about how you would handle the same thing if you had a really big linked list, like 20 elements maybe, which is not that big, but if you were trying to access like the 5th element in that 20 element list or the 10th element, you would have to iterate through every single one of the items in the linked list until you get to that index. So there's a relationship between the number of items in the list and how long it takes to access the values inside of the list. Therefore, getting an element inside of a linked list is actually kind of a painful process, and making it linear time to do that access, which compared to the array list, that's kind of a pain. In the array list, getting an object was super easy. You didn't have to walk through anything. It was just constant time. I guess this is kind of a reminder that this process of going through the linked list, going to the first item, looking to see if it matches, and then using the next pointer to go to the next item is called walking through the list. As you might imagine, it's similar to walking from one place to the next, taking steps one at a time. Okay. Any questions on linked lists and array lists? We looked at 2 operations, add and get, and we compared them. We saw that in the array list, the adding process took some more time than expected. We saw that it was linear time versus the linked list. If you're adding an element to the beginning, it's going to just be constant time. And then we also looked at accessing elements, right? Doing that get method. And in an array list, get method is constant time, very fast, very quick. And in a linked list, it's a little bit more annoying because you have to walk through that list, and it's linear time. Any questions on that piece? Looks like you're good. Mm. All right, so let's do our first coding problem. So first one is going to be practicing how to kind of walk through the linked list. We're going to give you some starter code and we're going to ask to override the string method, toString method, so that it prints out all of the elements in a linked list in a fairly elegant way. So here's the starter code. Brief overview, we've implemented the linked list for you. We have all of the items inside of the linked list. We have an add function that adds new elements to the linked list. All you have to do is create a toString method that will allow this system.out.println to print out like every single element in this um, linked list. Okay, so we'll do 15 minutes for that one. If you're done earlier than that, just message me in the chat. Cool. Let's talk at 6:35. Okay, looks like you are done. Very fast. Okay, cool. So let's copy and paste this over so it says that out. Okay. So we need to be able to print out all of the elements in the linked list. Public string to string. And then I'm just gonna add the override symbol here. Override. Okay, so first things first, you wanna find the beginning. Of the list, which is given here. And then you probably want to walk through the list and construct string with each value appended to the end. And finally, you probably just want to return the string output. Okay, so first finding the beginning of the list. That'll be the item I. Right, so this is just the beginning of the linked list, and that's pretty much all we're given. But we know how to go from the beginning to the next element in the list. And as always, maybe not as always, you guys probably might not know this, you will want to use a while loop ethically because you usually don't know what the size of the linked list is going to be. And there's different ways to construct the conditional inside of the while loop. Usually it's like you typically want to set it to be like the null value for either the next element or the null value for the current item. You want to check to see if you reached it. That's how you know you're at the end of the list, right? So I want to walk through this list, so that's why I'm having the while loop. And then I want to create a string with each value appended to the end. And in order to do that, I need to create a string outside of the loop. Good. Gonna be like an empty string. And what I'm just gonna do is every time we loop through, we're just gonna add it to the results. Results equal results plus I dot name. I dot name is just the value of that item. And yeah, we're just gonna add it to the end. And then we're going to go to the next element. In order to do that, we just reset the value. Okay. Okay. And then now we've walked the list and we've appended an item every time. And then we just want to return the see what happens when we run that. That's such a great, probably fun. No, not bad. Okay, so all right, it's printing out first, second, third, second, first. Just to make it a little bit more elegant, like we have it here, I'm gonna maybe add an arrow in between each of the items. I wouldn't want to do in the beginning. And I'm going to add a null at the end to indicate the end of the linked list. Okay. Now it looks much cleaner, right? Got the first, second, third, second, first, no. Okay, I think that was a pretty straightforward, simple one. Now let's kind of look at replacing an element in a linked list. So now we're going to use lambda expressions to do it. So you're going to go through the linked list and filter out any name that is flagged by the expression. So for example, if you have this expression, it should replace Jackie in all of the linked list items with the name Jackie inside of it and replace it with this string. And so we've got a starter code here for you. This is the functional interface called replace. It's got one method called replace that takes in a string and returns a boolean. And then you've got the function within the linked list replace, and replace will do this functionality here that we've described. And then finally, at the end, you can test this out with these 2 lines of code. So pretty straightforward, I think. And I guess this is some additional wisdom to take with you before you start the problem. Remember that you can use while loops to do your work for you, and that's just because for loops, you don't really know the size of the list in advance. So while loops are kind of a must, and if you find it difficult to kind of understand where you are in the linked list as you're walking through it, perhaps, then it might be helpful to just draw it out and imagine how you would walk through it if you were, writing it by hand, sorry. So yeah, that's it. So let's do 10 minutes to replace and just let me know in the chat when you finish. So 6:40, 6:43. Okay, so it's 6:43, so I'm gonna go ahead and review it. Did you feel like that question was more difficult than the other one? Or was it about the same? Or was it confusing because of the lambda expressions and stuff? Let's just move over this better code here so that we know what we're working with. I think it can be a little bit confusing, this, I think, line of code. And then when it combines with this line of code, how does all three of these pieces work, right? So we're asking you to implement the replace function inside of the linked list. And then here, what you're doing is you're calling linked list.replace, and then you're passing in the implementation of this functional interface that has replace as one of its methods, right? So you're calling replace, you're passing in the interface replace that you see up here. And then you're defining this function replace to be basically if it equals first, then return true. If it doesn't equal first, then return false. So that's what's happening if you look at the code overall. And I will kind of explain that a little bit more as I walk through it. So here in this second part, you're going to have a functional interface called replace, which we already gave you. And it's just got that one function inside of it, fully in replace string I, right? And you're calling the linked list function replace that you have to figure out and define for yourself. Is R. And it's calling it and is passing in the implementation for this functional interface right here. Okay, so let's talk about how we should implement the replace function inside of the linked list class, okay? So again, you're gonna need to get the first element, which we know how to do just from this previous exercise with toString. And then you're gonna want to walk through the linked list. So we need some sort of while loop here. And inside of the while loop, what you're going to want to do is you're going to see if replace inside of, if replace is true, then you want to change the name to be, I think we said it was deleted, right? Yeah, deleted. And then if replace is not true, else move on or ignore, right? So so the first part, get the first element, which again is defined for you in this linked list implementation, which is what the start here is. And okay. So we've gotten the start, and now we're going to go through the linked list. So that will just be a while loop. It's going to be conditional. Okay. And for this one, we want to keep going until we hit null, right? If we've hit null, if I equals null, then we know that we've reached the end of the linked list. I points to the current linked list elements that you're looking at. So while I is not equal to null, now you want to do this part, these two pieces of it. So if replace is true, so that's if replace R, so replace is confusing because the method replace here is the same thing as this, it's the same thing as this. So very confusing. But what you need to be thinking about is R is the interface, the implementation for that functional interface. You're going to call the replace method inside of R. And that method is this lambda function here. You got to pass in a parameter into that lambda function. What is the parameter? It's going to be the current value of name for that element, for the ith element, right? Here's name. You're going to check to see if that value is in fact equal to first. If that's the case, then you want to reset the value to be equal to deleted. If it's not the case that that's true, then you kind of just want to move on to the next element. Okay, that's pretty much all you have to do. You just have to go through, walk through the list. If it ever equals first, then you want to replace first with deleted. Yeah, let's just run it and see if it works. Errors, truly errors. Okay, so here we have it. First, and third, second, and then first is deleted, and then null. So it worked. Guess the confusing part here is maybe this line of code, understanding that this is calling the replace function that we defined here, and that basically allows us to check if first is equal to that ith element's name. And the reason why we do it this way, like obviously you could just take this and you could copy this and paste it over here and say replace is equals first, but then now you've hard coded what you want it to equal. So this is kind of a good example of why a functional interface and lambda expressions are useful, because you can define on the fly what you're going to replace. So if you had a different linked list and you wanted to replace all of the elements that actually had Jackie, for example, then you could just create another one of these and you could just say Jackie in here. Right? And you could just call this normally. You don't have to make any changes to this function and it would just work as normal. So that's a really neat trick there. It's a better example of it. Right. Okay. Cool. So let's move on. Adding elements to the end of a linked list. Okay, now it's a little bit, I don't think it's trickier necessarily, but going to be different from what you were doing before. All you got to do is loop through the linked list, get to the end, and add a new element. I don't know if we have server code. Doesn't look like we have any other server code. So go ahead and just attempt that. We'll do 5 minutes for this one and see what we get. Okay, I think it's been about 5 minutes. Um, but since we're kind of hitting the 7 o'clock mark, we'll go ahead and review this piece of it also. All right, so again, first thing we want to do is get that item. Then you want to do another walkthrough. Now, instead of going through and walking through past the end of the loop, past the end of the linked list, you want to stop at that last element, walk through to the end. And when you reach the last element, you want to reset the next pointer, the next reference for the last element to be a new item. That's going to be your last step. So again, let's just get item I, hold this start, and then walk through to the end, another while loop, except now instead of making I go till the very, so before we were doing if I is not equal to null, so we were going past the end of the loop. Like we got to the last element and then we went to the next element after the last element and there was nothing there, so that's when we stopped. But now I want to stop at that right before we hit that point. So I.next is not equal to null. So by the end of this loop, I should point to the very last element in the linked list. And if you kind of think about this and draw it out, maybe it might be easier to visualize why we're doing it this way. Okay, so while you're walking through the linked list, you're just going to do like an I.next every single time. So now after this loop, you should be at the last element, and then you want to set the last element's next pointer equal to a new item object, item. And if you just look at the constructor for item we have up here, we can just give it a name and a next. So the name will be the string that we passed in to add to end to S, and then the next value will now be null because we're now making this new element that we're adding the last element in the linked list. So you can make that null. So that should be it. Some semicolons here and there. Cool. That's the solution for this one. There's one more problem, and I think maybe we can quickly go through this one. It's an improvement to this add to element, but let's say that we had a variable called item last. So in here we have something called private item last. And the private item last is basically the last element in the linked list. And basically, we're going to ask you to add this snippet of code here. And we'll just add it here. So again, this is not stuff that you guys have to worry about, but this is just something we're giving you as starter code. And now we have this last element that we have access to. So how can we change this whole situation with add to end so that it's a little bit simpler, right? And I'm just going to give you the answer because we're running out of time. But before we had to walk through the end, find the last element, and then to the last element, we add a new item. But now we can cut that process down significantly. We have access like directly to the last element, right? We can just say this dot last, right? This is, sorry. this out last. I don't know. Okay, this, so we have access to the last element. We can just do this at last dot next. And we can, this is equivalent to doing this down here. And the same thing. And then we can just do new item and give it a new string and null value. It eliminates the whole process of using the while loop. And now we've added a new element to the list, but we want to make sure that we update this last pointer also, right? So that's this thing, date, point there, for the last element. And so that will just be this dot last equals last dot next. Okay. So this, I hope this is kind of easy and intuitive for you to understand. If not, just keep in mind that a lot of this is, if you're still like confused about linked list, if you just spend some time and walk through it by hand, it'll become more clear to you how these things work. Yeah, so you learned a lot of stuff today. Thanks for sticking with me, guys. We're at the top of the hour, so you're free to go. Next time we'll talk about maps. And then remember the solution's also available here. So thanks for coming.